get started anyway. I hope yesterday's lecture did not scare people off. So this is lecture number 4, and I posted the slides, including today's slides, on a web page of my own. So this address here, this URL, is where you can find these slides. So this is crypto CS as computer science, McGill CA, my name, tilde, my name, and Waterloo. So I realized yesterday that to a large extent, many of the basic crypto concepts have not been covered in any previous course, and that many of you may find it difficult to follow the crypto concepts. And so I just wanted to spend a little time to go through some basic crypto concepts and justify for you why we crypto people care so much about so-called semantic security. And so this is my last parenthesis, which will cover some basic notions of cryptography, and then we will get to lattice encryption, lattice-based encryptions. So let me just mention that in cryptography, we consider different types of attacks on crypto systems. So this is all about crypto systems. We consider different types of attack. The basic attack is the so-called ciphertext-only attack, where an adversary is given only a ciphertext. So the adversary sees the ciphertext between Alice and Bob, and the adversary is trying to establish what the corresponding message is. Now, this is the weakest type of attack, and to define good security, we will try as much as possible to achieve higher levels of security, higher than this one. So the other ones are non-plaintext attack. Non-plaintext means that for a while, the adversary finds out about the plaintext which is being encrypted and sent to Alice, and then some later plaintext M prime is encrypted, sent as an encryption C prime, and the adversary tries to determine what M prime is, given only its ciphertext, but also given a number of previous messages M encrypted as C, and being given M. So this scenario, as well as the following for chosen plaintext attack. In chosen plaintext attack, it's actually the adversary who chooses the messages that are encrypted by Bob to Alice. Now, in practice, this really makes sense, because in practice, for instance, in the Second World War, all planes had this little red book in it that seemed to be very important. And it was not really important, but it was really important for cryptographic purposes. If the adversary found such a plane and found such a red book, it was very tempting to think that it's important and make it and transmit it through cryptography. And this was exactly a chosen plaintext attack. The content of the book was chosen so that when you transmit it, you are actually making a chosen plaintext attack for your adversary. So if you manage to push data to Bob that Bob thinks he should encrypt, this is actually helping an adversary to do that. And the final type of attack, which is less frequently achieved, is somewhat surprising. It's known as a chosen ciphertext attack. And a chosen ciphertext attack is so that for a while, the adversary is going to choose ciphertext that are going to be decrypted for her. So for a while, the adversary is able to choose ciphertext and get them decrypted, and then this possibility goes away. You can imagine, this is sometimes called a lunch break attack, so you can imagine that during lunch break, you have access to the decryption machine, and then you go back to your office, and then you see some later message C prime, and you would like to decrypt it as M prime, but your access to the decryption machine is gone now. So if we manage to do that, this is like the most powerful type of attacks that we consider, but most of the systems that we, I mean, for instance, the system I presented yesterday and the system that I'm going to present today, they will achieve chosen ciphertext security, meaning that they resist to chosen plaintext security, meaning that they resist to chosen plaintext attacks.
Well,
yes?
Should it be obvious that chosen ciphertext attacks are stronger than chosen plaintext attacks?
It's not completely obvious. In a public key setting, it is, because in a public key setting, anybody can encrypt. So in a public key setting, anybody can do chosen plaintext attacks just by encrypting himself the messages. So in a public key setting, it's clear that if you can do chosen ciphertext attack, you can also do chosen plaintext attack because you can just do them. Okay? But in a private key setting, it's not that clear that it's actually more. Now let me answer this question. What is a secure encryption? And I will give you details about why and why we target for a specific security definition. But a first attempt is that an encryption scheme should be secure if no adversary can find the secret key which is used for encryption. Now, that's definitely a legitimate goal, but in itself, this is probably too strong a goal, because if you discover the key, of course, you break completely the system. But most of the time, we don't need such a strong security definition, and we could not actually achieve such a strong security definition. We're going to request something more specific, that an encryption scheme is secure if no adversary can find a plain text that corresponds to a ciphertext. So that corresponds to the 4 types of attack that I described, and depending on what happened prior to that, depends on the type of attack. Now this is not, well, this is a lot better because it focuses on plain text regarding ciphertext and no longer on the key. Getting the key is much harder than actually just decrypting a plain text. You may be able to decrypt a plain text without actually getting the key. But it would not be satisfying if an encryption scheme is only encrypting part of the plain text. If, for instance, 2/3 of your plain text is given for free, completely clear, and only 1/3 of the plain text is hard to recover, it would satisfy a definition of this type. So we want to say something more demanding, that no character of the plain text can be discovered from the ciphertext. Now, this is assuming that somehow what you're encrypting are words through letters and characters and so on. And of course, this is not general enough. So not only should it be that you cannot find any specific character of the plain text, but it should also be that you should not be able to derive any meaningful information about the plain text from the ciphertext. Now, this is basically what we're aiming for, and this is basically what semantic security is going to do for us. But the notion of meaningful information is too vague, because we don't have a formal definition for that. And so instead of going for meaningful information, we're going to go for all information, any type of information. And any type of information can be defined and used as any function of the plain text. So the final answer is, an encryption scheme is secure if no adversary can compute any function of the plain text from the ciphertext. And that's exactly what semantic security is going to be. Okay, so I'm going to give you a more formal definition of this in a few minutes, but when we do that, we will see that it's actually equivalent mathematically to some much simpler definition of security. So Shannon defined perfect security. Now don't look at this numbering. This comes from my crypto class slides, so that this numbering is sequential, but it's going to miss lots of stuff in between. Shannon defined security by saying that if you have an encryption scheme with its encryption, decryption algorithm, and the generation algorithm for the keys, you can define perfect security by saying that if you see a ciphertext, your probability distribution on what the plain text should be doesn't change. Now, achieving this definition is great when you can do it, but it comes with a lot of drawbacks. And so we're going to start from this definition to define secrecy in a computational setting, but we're going to look at some variations of this definition that are all equivalent and choose one which is appropriate for our setting. So a second definition is that the probability of the ciphertext doesn't change depending on the message that you are using. So if your distribution of the ciphertext is identical independently of the message that's being sent, then you achieve perfect secrecy. Now, of course, this property can be shown to be equivalent to the previous one. They both basically mean that the plain text and the ciphertext are independent of each other. However, this one is a bit more easier to adapt. We can say that, and again, this is equivalent to this definition here. We can say that an encryption scheme is perfectly secret as long as for every pair of plain text messages, M0, M1, the distribution of the ciphertext given M0 or given M1 is always the same. And this is getting a lot closer to where we're going. Yes?
So this, you assume that there is a randomness in the encryption and decryption, and that probability is over that.
Okay, so right now I'm assuming that in the eyes of an adversary, the messages that are being transmitted by one party to the other follow some arbitrary distribution. So the randomness actually comes from the ignorance of the adversary about what message is about to be sent. Now, one nice aspect of this definition, and the definition that's going to come next, is that you don't have to make any specific assumptions about this distribution. The distribution of the messages M0, M1, and so on can be an arbitrary distribution. You're not using any particular property of that distribution. So it might be that today, as an adversary, I have no clue what the people I'm attacking are going to say, and it might be that tomorrow I know that they're about to say yes or no. So my perspective can change very much. My uncertainty about the messages can change very much from one attack to another attack. But these definitions make sense whatever the distribution on the messages are. Okay? And so in a way, you're going to be right in the sense that in order to achieve strong notions of security, we will have to randomize the encryption scheme. But at this stage, it's not yet that. Okay, so this definition here gives us an experiment that we can describe and generalize later for computational settings. So we're going to define an adversarial indistinguishability experiment in which an adversary is trying to distinguish between the situation where M0 is sent and the situation where M1 is sent. And we're going to use this as the starting point for computational security that I will cover in a few minutes. The experiment is defined for a crypto system, a message space M, and an adversary A. And we define the private key experiment pi and A as follow. We have an adversary here who is trying to figure out the choice from a user about encrypting one of two messages. The two messages are selected by the adversary and are given to the user. The user defines a crypto system, establishes some keys, chooses a bit at random, encrypts one of the two messages MB, and give back this ciphertext to the adversary. And the adversary, well, first of all, the user outputs a bit B, saying which of the two messages were encrypted, and the adversary outputs a bit B prime, trying to guess what B was. And now the question is, what is the probability that B and B prime are the same? So how likely is it that the adversary is able to tell which of these two messages was actually encrypted by the user? So let me just go over this rapidly. This is the formal description of the experiment that I showed you on the picture. So we write that the experiment is 1, succeeded, meaning that the adversary was able to predict B reliably. So the definition that we're going to get from this essentially defines that an adversary is not able to succeed at this experiment with probability better than a half. So if we take the same experiment again and establish that the adversary's probability of success is a half, then this defines a notion which is equivalent to perfectly secret, and that we will use as an extension for defining security for computational situations. So this is a fourth definition for perfect secrecy. A system is perfectly secret if the success probability of an adversary in achieving this, succeeding at this experiment is 1/2. And we can show that definition 2.1, 2.2, 2.3, and 2.4 are all equivalent to each other, and we moved on to 2.4 because it's the one that can be easily generalized. Okay, so these four definitions are all equivalent, they're equivalent formulations, and we're going to use the last one in the computational setting. So in a computational setting, we will no longer have perfect secrecy. Actually, in general, in a computational setting, like the other schemes that we looked at, from an information theoretical point of view, the ciphertext gives away all the information. If you see a ciphertext, you know completely what the plaintext message is. But it's only your computational inability that prevents you from computing it. So the definition that we do for computational security uses, again, components of encryption, decryption. Okay, let me just go to the definition. We define an experiment which is similar to the experiment I just defined, but the big difference is that the adversary is now going to be an efficient algorithm that are represented by the flash character. The difference now is that the adversary is not allowed to run forever. He can run fast, but not for very long. And so now it's harder for an adversary to distinguish between the two possibilities because the adversary cannot run for as long as the original adversary did. So in a computational setting, we have a security parameter n, which establishes the level at which the system is going to be secure. We have then the same experiment in which the adversary produces two messages of its choosing, give them to the user who generates a key, who chooses a bit at random, encrypts one of the two messages, give the message back to the adversary, and the user outputs the bit, the adversary outputs a prediction B prime, and if it is the case that the probability that the adversary succeed in this game with probability no better than a half plus negligible, where negligible stands for a function getting smaller than 1 over a polynomial, then we say that the system is secure computationally. Okay, so this is our definition of computational secrecy. And it tells us that, so this is a description of the experiment. And we define computational secrecy in this way, that if you cannot succeed as an adversary better at this experiment than probability 1/2 plus something negligible, decreasing to a half as n gets bigger, then the system is computationally secure. Now, what does this have to do with the definition that I told you about, which is called semantic security? If you remember, semantic security follows from the initial definition I told you about, which is you shouldn't be able to come up with any function of the plain text. Well, this notion is formalized here, and I'll let you read the details of this slide later on, but it basically says that an adversary who is trying to predict a function f of m given an encryption of m, compared to an adversary A prime who's trying again to predict f of m without that encryption, will pretty much have the same success probability. So their success probabilities subtracted from each other is a negligible difference. So it means literally that your ability to predict a function f of m from the encryption is no better than your ability to do it without that encryption.
Sorry, what is H here?
Well, H here stands for extra information. So if you already know H of m about m, and you see an encryption, and if you see H of m without the encryption, your ability to predict f of m doesn't get any better. So it captures the fact that you can get this encryption in a context where you already know something about m, which is captured through H. And so this corresponds to this experiment where the adversary receives H of m information about m, receives a ciphertext for message m, and is trying to predict z, which, if possible, should be f of m. And we compare that to another efficient adversary, A prime, which receives H of m, but no ciphertext at all. That adversary outputs z prime, and we ask, what is the difference of the probabilities of these two adversaries in predicting f of m? And if the difference is negligible, then we declare this semantically secure. Now, semantic security was introduced by Goldwasser and Micali, and in the paper where they introduced the notion, they showed that this notion is actually equivalent to the experiment of indistinguishable encryptions in the presence of an eavesdropper, which is a definition which basically says that if I give you I give the adversary 2 messages, and he can encrypt one back that I cannot tell whether it's M0, M1, then the security I get with this definition is equivalent to semantic security. Now, for proving results and so on, semantic security is a lot more cumbersome because it refers to all these H's and all these F's and so on. So it's a definition which is a lot harder to work with, whereas the definition for indistinguishability of encryptions is a lot easier to work with, and for this reason, this is what is used in all security proofs because it's a lot easier to work with it. Okay, so this is the end of my parenthesis. I wanted to give you some grounds, some theoretical grounds why we are focusing on crypto systems where we're basically encrypting bit by bit and in such a way that distinguishing between the two possibilities is very hard. And so in particular, the system I told you yesterday was of this type. And the system I'm going to describe today is also of this type. So now let me address the last topic, which is lattice-based cryptography. And let me start by telling you a little bit about lattices. Okay. So given n linearly independent vectors, B1 to Bn, in Rn. So we're now dealing with real numbers, but in a few minutes I'm going to drop that possibility and move on to integers. But lattice problems in general are defined over real numbers. So given that you have n linearly independent vectors B1 to Bn, the lattice that's defined by them is going to be the integer linear combinations of these vectors. So we call L, in this calligraphic L of B1, Bn, the lattice associated to this set of BIs, which we call a basis of the lattice, to be the linear combinations with integer coefficients of the BIs. Now, it looks like this in 2 dimensions, and the right way to think about it is to expand this in n dimensions in your head, and it's basically the same type of feature. If you imagine in 3 dimensions, then there would be a replication of this in many layers in front here, and the layers would be shifted according to a 3rd basis vector that defines a basis element in a 3rd dimension, and you can go on and on to an arbitrary number of dimensions. So for instance, this is a lattice point B1, this is a lattice point B2, which are used here as basis, and I can get to that point by 1, 2, 3, B1 to B2. Now, in most applications in cryptography, we're not actually going to deal with real lattices, but with integer lattices, where the BIs are chosen from Zn instead of being chosen from Rn. But some of the computations involved may still be related to real numbers. Of course, we can't really handle real numbers. So we're going to be doing rational approximations of the real numbers. And there's a very nice book by Lovash, which expands on this topic very precisely and explains how we can do approximation through continued fractions so that we can approximate real numbers to a very high accuracy in polynomial time for all the basic operations that we need. So it's actually a book that I discovered recently, and I really like this book very much. Now, a lattice will, in general, have an infinite number of bases. There are very different ways of representing the same lattice. So for instance, this is the same lattice as before, except now that my two basis vectors, B1 and B2, have been selected differently. So now the point that used to be B1 plus B2 is now B1 plus B2 in this new basis where B1 and B2 are now much longer and much closer together. Now, somewhat similarly to what we did in coding theory, we're going to consider a bunch of problems that are analogous to those we did in coding theory. So a first hard problem, which is difficult to solve in general for lattices, is given a basis and some vector which is not necessarily, well, actually, which is not in the lattice, find the point in the lattice which is closest. So this is known as the closest vector problem. You're given the elements of a description of the lattice. You're given a basis, and you're given a point, and you try to find the xi's so that the summation of the combination of the bi's according to the xi's has a minimum distance to that point t. And now distances are computed in Euclidean distances. So the distance between point u and v is the square root of the summation of the square of the difference of the coordinates. So it looks like this. If you have, again, those lattice points as before, and this is a point t, then you should recover this particular lattice point here, and not any other one which is further. So this is very analogous to correcting errors in linear code. Now, the second fundamental difficult problem for lattices is to find the shortest vector in a lattice. So I give you a basis for a lattice, and finding the shortest vector in that lattice is to find the set of xi's integers so that the distance between the 0 point, which is in the lattice, because if you take all the xi's to be 0, you always get the 0 point in the lattice. So you're looking for the minimal vector which is in the lattice and is non-zero. So solving this problem is finding the coefficients xi so that the distance between the 0 vector and that vector is minimal compared to all other vectors. And again, we have distance which is defined in Euclidean distance. So again, this is very similar to finding a vector of minimum distance in a code, which relates to the minimum distance between any two code words. Now notice that in lattices, the shortest vector has always two representations because one is the negative of the other one. So there's always two shortest vectors in a lattice. But it's not going to be very significant in the future. Okay, so let me introduce a first approach to doing encryption using lattices. So the first proposal is from Goldreich, Goldwasser, and Halvey, and they suggested to do a crypto system in the world of lattices, which is similar to the McLeish-Niederreiter crypto system. In the original form that they introduced it, it was more like the McLeish crypto system, but in the version that I will describe now, based on Michencho's work, it is more related to the Niederreiter crypto system. So the private key of such a scheme is going to be what we call a good basis. Now, a good basis typically will consist of short, almost orthogonal vectors. And what is remarkable about such bases is that, for instance, if you have a basis which is almost orthogonal and with very short vectors, solving the problem of the shortest vector is generally easy because it's likely to be one of these vectors. If you have a basis which is all short vectors and all fairly orthogonal, then the shortest of them is actually going to be the shortest vector of the lattice. And also, solving the closest vector problem will be not so hard, and we will see a method by Babai, which essentially tells us that if you have a good basis, then you can do a computation which will give you essentially the closest vector easily. So the point of the system is very much as in McLeese cryptosystem, is we're going to start from a good basis and we're going to hide it and publicize a bad basis instead. So the public key of the system is going to be a bad basis of the lattice. Now, Daniele Miciencio, so in the original scheme, Goldratt, Goldwasser, and Halvey suggested to randomize the basis. But now we're working over integers. And so over integers, tossing random integers doesn't make sense. If we don't put any limits, tossing random integers doesn't work. Now, but you can still give meaningful notions to tossing random bases and get enough randomness out of that to make the problem difficult. But what Miciencio pointed out is that instead of picking the basis at random, let's pick one particular basis, which is known as the Hermite normal form of the as a basis, and this one is uniquely defined. So whatever the original basis B was, you can compute this Hermite normal form and obtain a representation which is a lower triangular basis for that lattice. Now, you basically use Gaussian elimination, and it produces this Hermite normal form, and because you're just using Gaussian elimination, whatever basis you start with will give you the same Hermite form. So this has the nice advantage that any attack that you can make to the Hermite normal form as a public key can be adapted to work on any other basis B prime of the same lattice, because all you have to do if you're given a B prime is to first apply the Gaussian elimination to get the Hermite normal form, and then you can apply your attack to that Hermite normal form. So in that sense, this basis is the worst possible basis from an adversarial point of view, because any basis that you would use can be made equivalent to that Hermite normal form. So if you choose the Hermite normal form to be the public representation, you have the worst possible public representation of that lattice.
Would this logic work for any normal form other than the Hermite normal form?
It would, as long as it's unique. Okay. As long as your output is the same for all bases. For instance, it's mentioned in textbooks that you can also have a upper triangular instead of lower triangular, and that will do the work equally well. So it doesn't matter which particular form you're using as long as it's uniquely defined. But a Hermite normal form will have another property that we're going to use, that Michencio used, and would not necessarily work for any form whatever. So the encryption process is, as in the Niederreiter crypto system, we're going to start from some point, lattice point V, and we're going to add noise to it, and the message that we're encrypting is somehow embedded in the noise. So this is exactly as was done in the Niederreiter version of the code base crypto system. Now, again, if we're going to select a random vector V to do that, we may have better ones and weaker ones. And it's, again, a problem. How do we precisely choose random lattice points in an integer lattice? Now, what Michencio suggested is that there exists a mechanism that we can apply to an arbitrary vector of this type. So if I have a lattice point plus an error r, I can always reduce it modulo the elements along the diagonal of the Hermite normal form public basis, and obtain a sort of signature which is exactly equivalent to the syndromes that we have in error correcting code. So if you take an arbitrary vector v in the lattice plus an error vector r, and you apply this process, you will always get the same value, whatever v is. So this is extremely analogous to syndromes. It means that every r will map into a value which is not r, but which is uniquely defined by r. So in order to compute this, you don't need to add any v at all. You can just start from r and use the Hermite normal form and compute that value. So the resulting vector is denoted r mod h, but it means this more elaborate process of reducing each entry of r mod the elements of the diagonal. And it provably, in a similar way as I said on the previous slide, it provably makes cryptanalysis as hard as possible, because r mod h can be computed from any vector of the form r plus v, for any vector v. So whatever particular vector you would use allows you to compute this r mod h. Now, if you think in terms of codes, this is exactly the same as, instead of telling you a code word plus a vec plus an error, I just give you the syndrome of the error. This is exactly the analogous notion. Now, to decrypt, one has to recover the vector v, or to figure out what the error r is from a ciphertext C. Okay, so a ciphertext is produced, as I described on the previous slide. You take a message, you somehow embed it in the error vector, and then you compute r mod h, which is going to be uniquely defined. Now you want to recover r from the ciphertext C. Now, the correctness of this crypto system is based on the fact that if you know a good basis, if B is a good basis of the system, then you can obtain, so if I give you any vector v plus r, not too far from some vector v, and if I have a fairly good basis representation of my lattice, then I can get rid of the errors by a very simple process described by Babai, which essentially is the following. So do these calculations over the reals, start from the basis B, compute B inverse. So the basis is an n by n matrix. Because it's linearly independent, it's invertible. So invert B, multiply B inverse by the vector V plus R. This is going to be close to B inverse times B inverse V plus B inverse R. The B inverse, if there was no R, B inverse V times B would just be V itself, because it would just be a change of basis which is undone and go back to the original vector. Now, it turns out that if the error R is small enough, the calculation of B inverse V plus R, if you take that in the integer part of it, you're going to get close enough to the value so that if you remultiply by B, you get back to V. So I'm not quantifying these things, I'm just describing them for you. But essentially, if you have a good enough basis, and if your vector R is sufficiently small compared to the lattice points, meaning that your V plus R is not too far from your V, then you can use this equation to do the decryption process. More or less, it's an error-correcting function which fixes the errors as we did in error-correcting code. And once you have obtained the integer B inverse V plus R, you can just reapply multiplication by B to get back to V. Now, unfortunately, well, this system has two weaknesses. One weakness is that it's now a completely deterministic scheme. Because if you start with some message R, or some message embedded as R, you start with a public basis H, which is completely known, and you compute R mod H, which is completely deterministic. And so the encryption of any message is deterministic. And so for this reason, it's actually impossible that the system is secure according to the definition I gave you, because a crypto system, to achieve this definition, must inherently be probabilistic. Now, why is it that it must absolutely be probabilistic? It's because if the encryption process is a known function of the plaintext, then there is a known function of the plaintext you can predict, which is exactly the ciphertext. Okay, so if you have a strong notion of security so that you cannot predict any function of the plaintext, then it must be that your ciphertext is a randomized process, meaning that even if I give you an encryption of a message, you still cannot predict any particular function of that message. Okay, so this is the first weakness. There's a second weakness, which is that nowadays, as I will tell you, we have systems where we have proofs of security that relates the difficulty of breaking the system to a specific assumption related to closest vector problem, or shortest vector problem. Whereas this one doesn't have this property, we don't have any specific relation between breaking the system and one of these hard problems. And finally, although theoretically the scheme is still unbroken, it's practically broken, in the sense that the sizes that were recommended by the authors were all broken except for one instance. And if you want to make sufficiently big lattices that will resist to the currently known attack, you have to make them so big that encryption and decryption is not very efficient at all. So it's not a theoretical attack because still you can still do encryption, decryption in polynomial time, and the attack is in sub-exponential time, but is not a polynomial attack. So if you take large enough values, you can still use the system, but from a practical point of view right now, it's not being considered at all.
So what is the underlying problem?
Sorry.
Shortest vector? Or?
It's finding the closest vector to a given point. So if you have well, you're not given v plus r, but you're given r mod h, which is analogous to having the definition of such a point, and you're looking for the closest vector from the lattice to that point. So if you manage to break the system, it doesn't necessarily imply that you're solving this problem because, but if this problem is hard, it gives you some hope that this system may be hard. Okay, so now let me define one notion which will make the system even closer to linear codes. It's a notion of Q-ary lattices. Q-ary lattices are defined as before by a set of n independent vectors, but it's called a Q-ary lattice if we are considering these vectors mod some particular integer q. Now, this is embedded in the lattice by putting extra basis vectors of the form 00q000. So if you take your basis b1, bn, and you add n new vectors of the form 0 everywhere except for 1q, it allows you to subtract and add q's as much as you like for every column, and therefore you can subtract and produce the mod q operation by adding and subtracting these vectors. Now, why bother about these in particular is because they have a very nice structure. The very nice structure that they have is that if you look at a hypercube of size q in all directions, it means that your lattice has the property that the lattice all over infinity is just replications of this hypercube. So if you look at this hypercube, you can copy-paste it everywhere around it, and that will produce exactly the lattice. Now, the difference with a general lattice is that in a general lattice, you might have to define a hyper rectangle or a hyper box, which is not a cube, but which has different length in each direction to obtain this property. So to obtain this property, so that this is a cube, you do that mod q, and then this is what you get. Now, the advantage of doing that is that every problem you can study regarding this lattice has a version in a finite domain. So instead of having lattices that are infinitely big, we're now considering lattices in a finite domain, which is this hypercube. Now, the advantage of doing that, or one advantage of doing that, is that we have now better definitions of picking random elements in the lattice and so on. And a lot of the operations that we can do are related now to this operation mod Q. So at this point, we have a structure which is very similar to linear codes, but not quite the same, and it comes with some diversity and some nice features that linear codes don't have. So we typically define two lattices associated to a specific matrix A. So if I pick an integer matrix A, which is n by m, I can define two lattices from it. One is called lambda q A, and the other one is called lambda perp, lambda orthogonal A. One is the set of words so that if I multiply A transpose by S mod Q, this is going to define a bunch of points Y. And basically, these are the lattice points corresponding to the combinations of A. Now I can define another lattice, which is all those points which are orthogonal mod Q to A, and this is a second lattice. Now it's interesting that these two relate to each other. Actually, they correspond. This first lattice corresponds to a generating matrix point of view of a lattice, and this corresponds to a parity check matrix point of view of generating a lattice. Now I'm going to tell you about the learning with error problem and about using that for cryptography. Now, learning with error is a particular lattice problem which has now become extremely popular. And the reason why it's become popular is because it has a lot of structure and it has an interesting relation to its security is related to the hardness of certain difficult problems in a very specific, clearly proven way. Now, one ingredient of learning with error is that certain vectors in learning with errors are going to be tossed with a discrete normal distribution that we call psi a bar, which is a discrete normal distribution of mean 0 and a standard deviation of q alpha and this constant. And we define the discrete form of the normal distribution to be as in this picture. You take elements with an actual normal distribution with this mean and this standard deviation, and you take its integer part and you reduce that mod q. So this is going to give you, sorry, this is the closest integer, not the integer part. This is going to give you a discretized version of the normal distribution. Instead of being a smooth curve, it's going to be a histogram sort of normal distribution. But it's close enough to the actual one to carry on properties that the exact normal distribution would have. And moreover, because we're reducing mod q, it's not ranging from minus infinity to plus infinity. It would range, say, from q over 2 to q plus 2, so sorry, to plus q over 2. And basically, to get this distribution mod q, you just flip back the next elements back on top here. And then you continue doing that, but they become so unlikely that this is roughly speaking what the curves look like. It still looks very much like a normal distribution, but it's been slightly modified by this mod q operation. Okay, now the reason why this particular error model is important to learning with error is because some of the results of proving hardness are exactly related to this particular distribution. If you pick an arbitrary distribution on the errors, it doesn't work. But if you work with this particular kind of distribution, you can prove a lot of things. So learning with error is a generalization of a problem that you may have heard about called learning parity with noise, which comes from the 70s and 80s. But learning parity with noise was restricted to Q equal 2 and to errors with Bernoulli distribution. So this is a much more restrictive case than learning with error. Learning with error is similar, but with a much broader set of possibilities for Q and distributions that are going to be of the type that I described. So the general learning with error problem is parameterized by a parameter n, which is going to be the size of the lattice, the length of the elements in the lattice that we describe, and an element q, which is the parameter so that we work mod q. And typically, this is going to be a polynomial in n that we're going to try to keep as small as possible, but to maintain security. So in learning with error, we are going to have a public information, a public matrix, which is A, which is an m by n matrix. We have a secret information S, and the goal is to find out S given some products of A and S. Now, if I give you some products of A and S and I don't put any errors, once I give you enough, if I give you the complete A times S, you can use Gaussian elimination to recover what S is. But if I add errors, somewhat like yesterday's scheme, it's going to suddenly get much harder. So if you toss errors with the distribution psi alpha bar that I just described, we get to the search version of LWE, which is that if you're given the matrix A, and you're given an erroneous lattice point P, which is AS plus errors, your task is to find S. Now, there's a specific constraint that alpha Q, so the alpha, which relates to the error probability of the distribution, and Q, the modulus, must satisfy that their product be roughly square root of n. Now, why the specific choice? Well, basically, it means that when we randomize on each entry of the lattice point, we're going to add little errors that are of magnitude much less than the value of Q. Because typically, if you have, say, that Q is n squared, then alpha is going to be much less than 1. It's going to be like 1 over square root of n over n squared. So typically, alpha is going to give you very low error rate. And so the errors that are produced through this are going to be very limited compared to Q. So the errors that you produce are never close to Q. They're something like Q over n or something like that. So they're much smaller, and so if you pick errors with this distribution, they never mess up your entries significantly. So if you have a point mod Q, each entry is modified a little bit, but never taken from one from one value to going very far. So the search version of LWE is given such a public matrix, secret S, and point P, which is erroneous, AS plus E, find the related S. Now there's also a decision version of the problem, which is given, again, a public matrix, given a secret S, and given that the entries are tossed according to the same distribution. The decision version is, if I give you A and P a point as AS plus E, or if I give you A and P where A and P are both uniform, then identifying which is the case is the decision version of LWE. Now, the reason why I point out this version is because it's actually equivalent to the search problem, in the sense that if you have an efficient algorithm for one of them, then you have an efficient algorithm for both of them.
When you say A and P uniform, uniform distribution? Or?
Uniform distribution over the elements mod Q. Okay, so these two are equivalent. It's clear that if you can solve the search problem, you can solve the decision problem, but it's also the case that if you can solve the decision problem, you can solve the search problem. Now, the crypto systems that we're going to see are going to be related to the decision version. And we can show that the crypto system is secure in a very strong sense unless you can break the decision version of LWE. Now, we know that that implies that we could break the search version of LWE. And it's been proven by Oded Regev that if you can break the search version of LWE, you can also break some worst case problems relating to the shortest vector problem. It's the gap shortest vector problem and the, sorry, I don't remember what the I stands for. But these problems, in the worst case, are very seriously considered hard. Nobody has any idea how to solve these problems. And what Oded Regev was able to prove is that a solution to search LWE on average gives you an ability to break these problems in the worst case. Now, the only glitch, if we, well, this is usually a glitch for theoretical computer science people, but the glitch is that the reduction is quantum. So the glitch is, in order to solve these problems in the worst case from this in the average case, the algorithm that does that is a quantum algorithm. But here we like quantum algorithms, so we're not bothered by this fact. And in practice, what difference does it make? Well, in practice, it means that this security reduction so far has only been proven in the quantum world. And if you have a quantum computer, then breaking this problem is equivalent to breaking this in the worst case. Now, that's a very strong statement. And it does not say that it's impossible to do it classically, but so far we don't have a classical version of it. Now, that's not entirely true. We have a classical version for gap SVP, but it requires in particular that the fields, sorry, the Q size, the size of the modulus, be exponentially large in N, which restricts seriously the application of it to cryptography. But if we believe that we're doing all this because we have quantum computers, then we have this very strong result that breaking the crypto system is actually equivalent to breaking these things in the worst case with the quantum computer. And currently, we have no reason to believe that we can break this problem with a quantum computer. Every attempt that we've made have failed. So let me complete this by showing you the learning with error system, crypto system, which was introduced by Oded Regev. And so it goes as follows. First, generate a private key S, which is an n-long vector, and choose an error, which is an m-long vector, sampled using the special normal distribution. This one is chosen at random uniformly, and E is chosen with the special distribution. The public key is a matrix related to a lattice, and we define the public key as this matrix A, as well as a point with error P, which is AS plus E. So this is the public key. The public key is the description of a lattice and an erroneous point not too far from the lattice. Now, an input message is going to be a bit B. The encryption of a bit B is going to be toss a random binary vector M. Now, this is somewhat unusual because we are working over the integers mod Q. So if we pick only 0, 1, we're actually tossing a vector A, which is very low weight, very low distance from the origin. The maximum length of this is the square root of M, which is much less than essentially most of the lattice points. So this type of A has a much lower weight, much shorter length than the vectors of the lattice. And so the encryption process is as follows. You multiply A by the matrix, and you multiply A times the vector P, which is the other part of the public basis, to which you add B, your bit, times Q over 2. Now, why Q over 2? Because the decryption process is going to try to establish whether this component is close to 0 or close to Q over 2. So if your bit is 0, this is going to be close. This will result in being close to 0. And if your bit is 1, this will result in being close to Q over 2.
Where does this A come from?
The little A is tossed at random at the time of encryption. Okay, so you pick. So you can visualize this by saying that this here is a scalar product between the vector P and the newly tossed vector A. So that's going to be a number mod Q, this product, to which you add or not Q over 2. Now, the decryption process is going to try to cancel out this PA using that other component AA.
Oh, you're taking the inner product between AA and PA. Plus
No. This is a couple. This is a pair.
Yeah, okay.
So this is a pair. In the first part, you have a new vector, AA.
Yeah.
In the second part, you have just one value, which is the product between P and...
P is a vector.
Yes, capital P is a vector of length M.
Okay,
Yes.
thank you.
Okay, because it's a vector times, it's A times S, which is a vector. Now, the decryption process is going to yield 1 if and only if the difference between, okay, if you receive a pair UC, okay, this is producing a pair, if you receive a pair UC, then subtract S times U from C, and depending if you're closer to Q over 2 or closer to 0, then define your decryption to be 1 or 0. Now let me, for a second, follow this for you. What do we get if you take C minus S transpose U? Well, C is supposed to be P transpose A plus B times Q over 2. So the first part here is P A plus B times Q over 2. Minus STU, U is supposed to be A, capital AA. So S times that is capital SAA. Now, by definition, A transpose S transpose A transpose is the same essentially as AS. And so I guess there should be a transpose on my error here, but let's ignore transpose. Essentially, this SAA is going to yield PT, okay, because AS plus E is P. This SA is actually PTA plus the error EA, which means that the PTA part from here and here are going to cancel each other. And so because the decryption process, the person decrypting knows S, he can subtract this from C, and that will yield BQ over 2 plus E times A. Now remember that E is one of these vectors who sampled from this special distribution and which yields error of a small weight. This A is thought to be a binary vector, which is also a vector of short length. If you multiply both of them in a scalar product, and this is what this is doing, you're going to get a scalar product which is rather small. And therefore, the nearest integer to B cubed over 2 plus this small fudge factor, fudge term, the nearest integer is actually going to be the correct BQ over 2. If it's close to 0, then it means B was 0. And if it's close to 1, then it means that B was 1. Sorry, if it's close to Q over 2, then it was close to 1. Now, what is remarkable about this system is that we can show that breaking it is equivalent to breaking LWE in the decision version of it. So the first part in proving that shows that distinguishing between the public key AP produced according to the distribution where P comes from errors E according to our special distribution is indistinguishable from a uniform pair AP where P is tossed uniformly instead. So this is the first part of the proof. You have to establish that the pairs AP with the special distribution are actually undistinguishable from pairs AP where P is completely uniform. And once you've shown that, you can use a second part and essentially demonstrate that if AP were actually chosen uniformly, then the second part, Once you get the encryption, you see as well as AP, if you encrypt using a completely uniform A and a completely uniform P instead of a P of this type, then UC actually carries no information about the bit. So you can show that if you take M large enough, then if A and P are completely uniform, not tossed according to this special distribution, but completely uniform, then your encryption is actually equivalent to a one-time pad, and you're encrypting completely, and you don't have any information available about the plain text. But this works only if m is more than n log q, but that's not too much of a constraint. So together, these two results establish that the system, the crypto system, is secure under chosen plaintext attacks in the very strong indistinguishability sense, as long, through these reductions that I mentioned before, as long as the gap SVP and the SI or the SIVP are hard in the worst case, which is a very, very strong result. We had never seen in cryptography any result of that strain before. So these things that we can do with LWE, the kind of proofs of security that we can get, are much stronger than the previous proofs of security that we could do before. For instance, with RSA, we could prove something like there's a form of the RSA system where we were able to prove that if you can break it, then you can break RSA for the same modulus and the same exponent. But we never had a proof which establishes that if you can break it for any modulus and any exponent. And this is sort of the flavor of this proof now. This flavor is referring to the worst case difficulty of a problem and not the average case. So if you can break this system, then you can break some problems in the worst case. And that's a lot harder than the average case. Let me skip this. It's very similar, and I just want to conclude now. Now, I borrowed this slide from Chris Picart, who justified his work because he is one of the people extensively working on the crypto systems based on learning with errors. He justified the importance of his work, and I fully agree with him, by the fact that before 2005, there was no crypto systems about based on LWE. Now, in 2005, Oded Regev came up with his crypto system and his proof that relates the difficulty of breaking the system to the hard case, the worst case difficulty of some problem. Now, it took about 3 years for people to realize that something interesting was going on. So this is a number of papers that were published on the vertical axis, and this is the year on the right, on the horizontal axis. Now, in 2008, there were 3 papers that related, it introduced new cryptographic applications of LWE or showed new features of LWE that are relevant to cryptography, and then it just exploded. It just, suddenly within a few years, there were like 10 important results regarding LWE. Now this slide is taken from 2012. It may seem that 2012 was going to be a bad year with respect to the previous one, but this talk comes from February 2012. So in February 2012, there was almost as much as the previous years. And so the whole year was something big like this. The important point I want you to go home with is that LWE is believed to be very hard. It's believed to be hard for good reasons, because it's related to the worst case of some, I keep referring to when these words were here, these 2 problems in the worst case. And it has very nice properties. I did not mention all the nice properties, but LWE is random self-reducible, which is part of the process of proving that the average case LWE implies the worst case of these problems. LWE is a great invention for cryptography. It gives us a number of features that we couldn't do before. In particular, the hardness proof had never seen that good. We can do, using variations of LWE, we can do homomorphic cryptography. It's a great tool, and I think this is, of all the things I presented this week, is the most important of them and the most useful of all of them in terms of security results. And practicality is moving in slowly, because all the discussions I've done so far are not so much about how practical is it when you really want to implement them, but there have been some recent improvement to reduce the size of the public key and so on, which is making it quite practical nowadays. And one of the main messages for this week is learn more about LW. It's a very important post-quantum. Even pre-quantum, it's doing a lot of things that did not exist prior to these studies. And so this is my conclusion. And let me just leave you with a reminder where you can get my slides. It's been a pleasure to get this done. I wish that in the future, the scheduling of the courses is so that everybody gets an introduction to cryptography before I do this class. I sort of realized at the end of the first day that some of you never had a crypto training, even of the basic things of crypto. And I wish that in the future, this is organized so that I can teach to a group which already knows the basics of crypto. But otherwise, I really enjoyed it, and I thank you very much for showing up all these days. Thank you very much.